All right, 4.3, Riemann Sums. So we have this beautiful guy. His name is George Friedrich Bernhard Riemann. All right, and Miller, I see her looking at him, so Miller's going to read for him. Riemann.
Did most of his famous work in the areas of
Euclidean
geometry, differential equations, and number theory. Riemann's results in physics and mathematics that form the structure in which Einstein's general theory of relativity is based.
All right, fantastic. So we didn't get to contribute his name last year. We just called him rectangles. But it's actually made by this dude named George Friedrich Bernhard Riemann. So if you ever need names for children later on in life, those are all good choices. Those are all good. Pick one. All right, George without the E, doesn't matter. Friedrich, that's pretty awesome. Friedrich. And then Bernhard, that's a classic. That's a classic. All right. So anyway, the crazy thing to me is like he did this in 40 years of his life, and like honestly, like I don't know, people don't really do anything in the first 10, so it's like he did pretty good. And thank goodness for George. All right. So I want to talk about rectangular approximations. Thanks to George. Which one's the closest? Which one's the closest to the area under these curves? The yellow. Why is the yellow?
Because it has
more space covered. Okay. More rectangles. What happens to our widths? They get smaller. That's what happened here. All right, so let's play along. We're going to find the area under these graphs. All right. So what we're going to do is I would make them into rectangles. So what's the area of that first rectangle? 4. What's the area of the next rectangle?
6.
Look at you guys. Then?
2.
Then?
10.
All right, and then we add them all together. So what would be the area under that curve? 22. All right. All right, and then the next one I'm going to make into some rectangles. So I personally would kind of make it there, and then there, and then there. That's personally how I would do it. So what's the area of my first rectangle? I think that's your favorite.
6.
All right. And then what do we get?
6.
Then we get?
3.
And then we get? 12. Very good. And then we add them all together, and what do we end up getting? 26. Very good. All right. Pretty good? All right. If we can do that, we can do lesson. All right. So we're going to do rectangular approximation method. Riemann sums is basically what it is. Okay. So last year we just called them rectangular approximation methods. Now we're going to call them Riemann approximation methods. I need some readers up in here. And you know what? Riley's going to be our reader.
Suppose we wanted to know the area of the region bounded by a curve, the x-axis, and the line x equals a and x equals b as shown at the right. The first step is to divide the interval from a to b into subintervals. We can then draw a rectangle using the width of each subinterval as the base. The height of each rectangle is determined by the function value at a point in a specific subinterval and can be determined using 3 different methods. We could use the left endpoint of each subinterval called LRAM, the right endpoint of each subinterval called RRAM, or the midpoint of each subinterval called MRAM.
All right, fantastic. But the first thing we need to find is we need to find the width of each rectangle. And so the distance between these two x values, how would we find the distance between those two x values? How would we find that? B minus A. We do B minus A over how many rectangles we're going to have. So B minus A over N. That is how we would find the width of each rectangle. If they're equal widths, that's how we find it. All right, let's put it into practice. Here we go. So now we're going to use 4 rectangles to approximate the area under the graph of y equals x squared minus 2x plus 2 from x equals 1 to x equals 3. You should probably write that function out. All right. And we're going to use LRAM, RRAM, and MRAM. First one we're going to do is we're going to find LRAM. But before we do that, we need to find the width at which we're doing. So what's my B? 3. So I'd have 3 minus, what's my A? 1 over how many partitions are we making? 4. So what's the width of each of these rectangles? 0.5. All right. And I am actually going to use decimal right here. I know that's kind of weird. So the first one, if I do an LRAM, I'm going to start from my which way? The left. So I'm going to start over here at 1. So I have a width of 0.5, and then I'm going to find f of 1. And so that kind of goes over there. And then what would be my next function value that I need? F of what? F of 1.5. And then plus f of what? What would be my next function value? F of 2. And then plus f of what? What would be my next function value? 2.5. And then f of? No, we're done. All right, because if I kept going, I'd actually go past 3 because I'd be going from the left. All right, so now we just need to get our numbers going. So I have 0.5 times, what is f of 1? 1. All right, that was a nice easy one. Now, I need to find f of 1.5. Now, you can do this without a calculator, but we can use a calculator. Now, this is the way I'd encourage you to do it. I'd encourage you to graph this function. So I want to show you how to use your calculator. Let's work smarter, not harder. So graph this function. So x squared minus 2x plus 2. Now that we have it graphed, go to second calculate, and then value is the first one that comes up. So second calculate value. And what do we want the value at? What x value? 1.5. So let's just press in 1.5 and press enter, and it should shoot out a y value to us. All right. And so what would be that y value? 1.25. Now, I know that this one isn't too bad. This one isn't too nasty of numbers. However, this is a good technique to use for really nasty functions. All right. What would be my f of 2? We can do the second calculate value and then substitute in 2. Press in 2. And so we end up with 2. And then we need 2.5. So do the same procedure. And we end up with 3.25. We press that into our calculator and we end up with 3.75. All right. Now, I want to talk about this a little bit right now. Is this an under or over approximation from the area under my curve? It's an under approximation. Now, I'm not going to get into the specifics of it yet, but why?
Because it's leaving space.
Leave space. Doesn't have my gaps. All right. So that's all I'm good with right now. All right. Let's do our RAM. So now, which way are we starting from? The right. What's my width still? 0.5. So now I have 0.5 times f of what? 3. And so I'm going from the right. Wow, that's not a straight line. And so then, if I go down, I'd kind of have that kind of rectangle. And then what would be my next one? F of 2.5. And then what's my next one? F of 2. And then what's my next one? And then what's my next one? No, we don't keep going. All right. And so I have most of these, but I don't know f of 3 yet. So let's put in f of 3. So find the value at 3 on your little graphy graph. And what do we end up getting? 5. Plus,
3.25.
we already have these. And then 2 is 2. And then 1.5 is
1.25.
And then we have to do a little bit of math on the front screen of my calculator. And we end up with 5.75. All right. Now, again, I'm not going to get into this too much, but is this an over or under approximation?
Over.
This is an over approximation. All right. Pretty good? Okay. All right. Now we're going to do an MRAM. What is the width of this MRAM still? Still 0.5. However, it's in between. It is in the middle, the midpoint of my width. So if my first width is going to go from 1 to 1.5, right? It needs to go in the middle of it. So what would be the height or the function value of the middle? F of 1.25. Very good. So I'd have to go up in the middle, and then that's my width of 0.5. And so then I'd go up in the middle of what?
7.5.
F of 1.75. And then plus F of 2.25. And then F of 2.75. And so this is where, if we graph it, this is going to be a lot quicker than putting all these nasty numbers in your calculator. All right. So what is F of 1.25? Good. And then plus, what's F of 1.75?
1.5625.
Good. And then F of 2.25, we end up with?
1.5625.
Good. And then F of 2.75 is? 625. Good. And then we have to do a little bit of math, and we end up with?
4.625.
Very nice. All right. We're going to have Josiah go for it.
It is necessary to have a graph to estimate the area.
Is not.
It is not necessary
That's kind of a big deal.
to estimate the area. Suppose the table below shows the velocity of a model train engine moving along a track for 10 seconds. Using LRAM with 10 sub-intervals, estimate the distance traveled by the engine in the first 10 seconds.
All right. So I'm given velocity. And I have to go back, and I need to estimate what? Distance. All right. Which basically means I need to go backwards. All right. So I basically need to find the area under that velocity curve. All right. That's what's actually happening here. So what's going to be my width? What's my B, first of all? What's my B? 10. What's my A? 0. All right. And then how many intervals am I having here? 10. So I have 10 minus 0 over 10, which is 1. So my width on this first one is going to be 1. And so now I need to find my value from the left. So I'd look at this 0. So now I have 0 plus, what's my next one? 12. And then plus 22. And then 10. And then
5.
and then
13.
then
11.
then
6.
then
2.
then
6.
and then
None.
that's it. All right, now it wouldn't affect it on this one if we had 0. However, it would not be it. So we do some quick math, and we end up with 87 centimeters. Congratulations. I'll do that for you. Now I want to do another one. I want to find an MRAM, not MRAM. I want to find an RRAM, okay, a right-hand Riemann approximation with 5 subintervals. I want to find a right-hand Riemann approximation with 5 RMAM. All right, bless her heart. All right, so I'm going to have 5 subintervals here. So what would be my new width? It'd be 2. It'd be 10 minus 0 over 5. So I'd end up with my width of 2. So now I have to go backwards. So I'm starting over here. Does that make sense? So now, what would be my first one that I'd be using? 0. So I'd have 0 plus, now this would be my next width. So it'd be kind of going from 8 to 6 kind of thing. And so, what would I be using now?
2.
The 2. And then
11.
I'd use 11. And then I would use 5. And then I would use 22. And then I would use, no, I'm not using anything more. All right. And so we'd have to do a little bit of math, and I think we'd end up with, what is that, 80?
76.
I think it's 80. 80 centimeters. All right. All right. All right, the next one. I'm going to use MRAM with 5 subintervals. All right, so I'm going to use MRAM with 5 subintervals. So Again, what's going to be my width? 2. So my width is still 2. However, an MRAM, a midpoint Riemann, is going to be in the middle. So what value would I be using here? It'd be 2 times what? 12. And then 10. Because it's in the middle of them. And then 13. And then
6.
and then
6.
there it is. All right. And so we do a little bit of math and we'd end up with 94 centimeters. All right. We pretty good there? All right. All right. So I'd like you to draw up this little table. All right. So we have a table of values, x values, f of x values. And then I need to approximate my integral using a left hand and a right hand. Riemann. All right. So the first one I'm going to use is a left hand Riemann. So the first one we're having is a left hand Riemann. Now, what do you notice about the width? 0 to 2, 2 to 3, 3 to 7. Are they the same? Are they equal? No. Okay, so I can do an LRAM. I can do an RRAM. Later I'm going to do a trapezoid. But can I do an MRAM? No, I can't do an MRAM unless they have equal widths. All right, but I can do an LRAM. So what is the width of my first one? I go from 0 to 2. What's my width? 2. But then what value do I use because I'm going from the left? I use 3. So 2 times 3. And then what's my new width? 1 times what's my new value I'm using? 4. And then what's my new width? 4 times 6. And then 3 times 5. All right. And then we have to do a little bit of math. 2 times 3 is plus, and then plus 15. We add them together and we end up with 49. It was close. That was close, TJ. All right. And then we're going to do an RRAM.
Oh.
All right. So a right hand Riemann. So now we're going from the right. So what's my width? 3. And then what do I use? 6. And then what's my new width? 4. And then I'm using 5. And then what's my new width? 1. And then I'm using 6. And then my new width is 2. And I'm using 4. So we have to do a little bit of math. And TJ is going to help me out. 3 times 6 is?
18.
Plus?
20.
Good. Plus?
6.
Love it. Plus?
8.
8. And we add them all together and we get 31. I'm just kidding. All right, what do we get? 52. All right. All right. Fantastic. Now, I want to show you a caution thing that you should be aware of. I wish I did it on the homework. I thought I did, but I didn't. Sometimes the integral will be something like 0 to 7. However, what does our little chart go to? 10. So what they're doing is they're trying to trick you. All right? You don't even need this box if they go from 0 to 7. Does that make sense? Yeah. So I am going to put one like that on your tests and quizzes because I'm so mean. I'm trying to trick you. Am I really trying to trick you if I'm telling you right now? No. However, you need to be looking for those things. Does that make sense? All right. So if I were to go from 0 to 7, how many of them would I actually have? How many rectangles? I'd actually only have 3 instead of 4. Okay. So you need to be looking for that. It's just a little change in the number. All right. All right. Cool. All right. Riemann worksheet. It is on Canvas.